Okay, I'm just on my computer. Can you hear me?
Yeah, we can hear you. Can you hear us?
Okay. Yes, I can hear you. I
Okay.
think for the time being, I'll just use the computer and then we'll try to fix it while Richard gets started because I don't want to hold us up
Okay.
too much.
Yeah, I think just one more minute, maybe Kate, just to
Sure.
let people finish popping over, and then yeah, go ahead and kick it off whenever you're ready.
Okay, sounds good. And Aaron, you started recording, I believe. It looks like you're recording.
Yep, I started the recording, so go ahead and get
Okay.
started whenever you're ready.
All right. And Richard, you all set to go? Seeing you currently.
Yep, ready.
Okay, you're there. Okay, cool. All right. Well, welcome everyone to the first lecture series of the new year. And we're very excited today to welcome Richard Cartwright of APL, who will speak to us today about JWST, revealing spectral tracers of recent surface modification on Europa. And Richard, as I give a little intro to who you are, you want to bring up your slides? That would be great.
Sure.
But Richard is a senior professional staff member at Johns Hopkins University Applied Physics Lab. He spent the past 15 years studying icy moons and ocean worlds. His PhD and postgraduate studies have largely focused on investigating the compositional links between the surfaces, atmospheres, and interiors of icy bodies. In recent years, he's focused on the analysis of JWST data, contributing to projects for investigating moons and rings of Jupiter, Saturn, Uranus, as well as TNOs and irregular satellites. And he's also a member of the Habitable Worlds Observatory, Community Science, and Instrument Team. And with that, take it away, Richard.
Thanks, Kate. And thank you for inviting me to give a talk as part of this Clipper seminar series. I'm certainly excited to be here to talk about Europa and JWST results for Europa. And off the bat, I just want to highlight that the results I'm going to discuss today were published last year in PSJ. For folks who have heard me talk about Europa in recent conferences, such as at AGU last year, rest assured, because this is a long format talk, that I'm going to have some additional topics that I haven't covered previously, so there will be some new stuff. But to start off with, why are spectroscopists so interested in this particular region on Europa's surface? Talking here about the leading hemisphere, which JWST observed in 2022, with those observations focused on Tara and Powys, as well as an ice-rich zone that's kind of nestled in between them, has distinct geologic features on its surface compared to the chaos-dominated Tara and Powys, and has a distinct spectral signature as well. And from the spectroscopy side, one of the more exciting results includes the detection and characterization of irradiated sodium chloride on Europa's surface, which seems to be concentrated in and around Tara Regio, suggestive of subsurface surface exchange, whether that's sodium chloride from an ocean at depth or perhaps from liquid water pockets trapped in Europa's ice shell closer to the surface, is something that we can't discern using spectroscopy. Nonetheless, sodium chloride is not stable over geologic timescales on the surface of Europa, so it has to be replenished from the subsurface by one mechanism or another. Now, of course, as an icy satellite, Europa's surface is dominated by water in the form of ice, or also in the form of hydrated minerals. We've diagnosed the presence of crystalline ice on the surface of Europa for decades now, primarily through the identification of a 1.65 micron crystalline ice band, which I'm going to continue to come back to throughout this talk. So this plot shows you a global spectrum of Europa's leading hemisphere collected by NIMS on Galileo, compared to two simple models, one of crystalline ice and one of amorphous ice. And ground-based data has largely backed up these Galileo NIMS results for the past few decades. So this stack of IRTF spectra I just put up goes from the leading hemisphere at the bottom of the stack in terms of increasing longitude, west longitude, as you go up the stack, going across the trailing hemisphere of Europa as well, just highlighting that the 1.65 micron band is detected across its surface, and the central wavelength doesn't shift much at all. The intensity of the feature changes. It's certainly weaker on the trailing hemisphere compared to the leading hemisphere, but nonetheless, it's omnipresent. Now, we can also use longer wavelengths to diagnose the nature of water ice in terms of amorphous or crystalline, using the water ice Fresnel region between about 2.9 and 3.3 microns. In particular, near 3.1 microns is a diagnostic crystalline ice Fresnel peak, which we see in synthetic models, and we see it on icy bodies across the solar system, but we haven't seen it on Europa, at least not in the NIMS data or in the available ground-based data sets. And so there's a bit of a disconnect here, where at one wavelength range, we see evidence for omnipresent crystalline ice, but then at another wavelength range, it looks like Europa's surface could be dominated by amorphous ice. Well, a simple and fairly elegant hypothesis put forward by Hansen and McCord in their paper from 2004 suggests that Europa's surface could be vertically stratified, where crystalline ice is retained at depth, and we sample that ice spectroscopically through the 1.65 micron band, whereas the Fresnel region samples much shallower depths. If we want to be generous, maybe the top 10 microns of Europa's surface, but once you get into the Fresnel peak region, you're talking about maybe a micron. Really, you're just talking about photons getting reflected off the facets of exposed ice grains. And so perhaps then the exposed surface of Europa is dominated by amorphous ice, and then as you go to depth, you find more and more crystalline ice. And this hypothesis has hung together reasonably well for the past few decades, but it's worth noting that NIMS data and ground-based data, in terms of their sensitivity, in terms of their signal to noise, they fall off a cliff past 2.5 microns. The data get pretty ratty in the Fresnel region. And so it's certainly possible that there is a Fresnel peak on Europa. It's just the quality of the data was insufficient in order to detect it. In steps JWST, an extremely sensitive platform over near-infrared as well as mid-infrared wavelengths. I'm sure this audience has already seen several talks, especially related to the results for CO2 in the 4.3 micron region, which we're going to discuss a little bit toward the back end of this particular presentation. And in fact, JWST is so sensitive that at shorter wavelengths, it completely saturates on the disk of Europa. Now, we were able to reduce these data, reduce the number of non-destructive reads fed into the calibration pipeline, and claw back some of this wavelength coverage, crucially including wavelength coverage for the 1.65 micron crystalline feature. And so with one platform, we can look at crystalline ice or amorphous ice in the 1.65 micron range and in the Fresnel region for the first time since NIMS did this back in the early 2000s and the late 1990s. So after re-reducing these data, the first thing we did is generate some regional spectra over regions of interest, which includes Tara, Powys, and again, that north latitude ice-rich zone, which is nestled in between them. And then without further ado, the data are absolutely crazy from a signal to noise perspective. They really are a large improvement over what has been previously made available through different platforms. Now, there's a lot going on this plot. I'm going to come back to some of these other spectral features later on. But for now, I just want to simplify things and continue the discussion on the 1.65 micron feature versus the Fresnel region. So after generating these regional spectra, we compared them to other existing data sets, including ground-based data collected with the IRTF, as well as that global leading hemisphere spectrum I showed previously, put together with NIMS data. And then we also compared these empirical data sets to synthetic spectra generated using optical constants for water ice, both crystalline ice and amorphous ice from Mastrapa et al. 2008 and 2009. Note, we are not trying to fit Europa's continuum using these synthetic spectra. We're just interested in diagnosing the presence of crystalline versus amorphous ice in key wavelength ranges. So really, we're looking at band morphologies and essential wavelengths with these synthetic spectra. And looking at the 1.65 micron feature, we find that it's in all of the data. That's not a surprise. It's totally consistent with all the other data sets that exist for Europa's surface. The feature seems to be strongest in that ice-rich north latitude zone and weaker in Powys, and then weaker again in Tara. Now, we do see some interesting results in the Fresnel region, where that north latitude ice-rich zone, we don't see a Fresnel peak, again, consistent with amorphous ice, so supporting previous results. But in Tara, and maybe also in Powys, we actually do indeed see a small Fresnel peak near 3.1 microns. And so it looks like our results confirm that Europa's surface is vertically stratified with amorphous ice at the exposed surface and crystalline ice at depth. But in Tara, perhaps something more complicated is happening. So after comparing the data, the median spectra to synthetic spectra and to other global data sets, that we then set out to spatially map these different spectral features. So I'll show you those maps, starting with the 1.65 micron band. That oval that popped up just shows the rough location of that north latitude ice-rich zone. Highlighting here, starting on the left, the central wavelength of this feature is not deviating much at all. It's pretty much locked to 1.651 or 1.652 microns. But the feature is stronger in that north latitude ice-rich zone and weaker in Tara and Powys. So far, so good. This is hanging together with previous data sets. When we get into the Fresnel region, this is when things start to get a little bit funky. The central wavelength starts to shift around a little bit more. And in fact, this feature is stronger in Tara and Powys than it is in that north latitude zone. And then when we get to just measuring the 3.1 micron Fresnel peak, we only reliably detect it at the 3 sigma level in Tara and maybe a little bit in Powys. We don't see it at all at those northern latitudes. And so getting back to this story again, what exactly is going on with water ice on Europa's surface? We seem to be confirming the presence of a stratified, vertically stratified regolith with amorphous ice at the exposed surface and crystalline ice at depth. But in Tara, we're also seeing crystalline ice at its exposed surface. Now, our first idea was maybe there's a difference in charged particle populations. Maybe that north latitude zone is more heavily amorphized, but that quickly fell apart. It looks like charged particle populations hitting these regions of the leading hemisphere, all at low latitude within 30 degrees of the equator, are roughly the same. And we calculated some estimates and found that to be the case. But another possibility is a process called thermal recrystallization, and maybe that's what's driving this difference. So other studies that have looked at the bond albedo for these different regions, as well as their porosity using platforms such as ALMA, found that Tara and Powys are notably darker than the ice-rich zone and also likely have more porous regoliths, where a study led by Mitchell and colleagues from 2017 showed that at low latitudes on Europa's leading hemisphere, a porous regolith could recrystallize on the order of about 2 days or so if it started off as dominantly amorphous, whereas a more compacted regolith may take more like 30 to 40 days in order to recrystallize. We estimate that amorphization processes could take about 2 weeks or so for exposed crystalline ice to become dominantly amorphous. Or in other words, putting all of that together, our results suggest that, or support that Tara and Powys are darker and more porous, and therefore recrystallization is able to outpace amorphization processes at the exposed surfaces of these chaos-dominated regions. Whereas in the ice-rich zone, it's brighter, it's colder, it could be more compacted, and in this zone, amorphization processes outpace recrystallization at the exposed surface. And so this is a summary of this part of the project, but really I think the key take home here for future studies is that the Fresnel region is an incredibly sensitive indicator of what's happening at the very top, at the exposed surface of icy bodies. And it'll be really interesting to see what JWST is able to do for Europa, as well as other icy satellites over the next few years or so. And then, of course, once Clipper gets to the Jupiter system, I'll be very interested to see what MISE is able to tell us in terms of the Fresnel peak and how it changes on Europa, as well as the other icy Galilean satellites. So now I'm going to switch gears here to talk about some of the other results that came out of this study, thinking about contaminants, primarily hydrated minerals that could be mixed with water ice, and how these contaminants could be changing the band morphologies and wavelengths of the water ice features that we've been investigating. And I'm going to start with the 1.5 to 2.2-ish micron region, and then we're going to switch to talk about the so-called 3.6 micron continuum water ice peak. So looking at these shorter wavelength features, starting in the 1.7 micron range, we see some hints for a deviation from pure water ice in this range. Maybe even if you squint your eyes and look at the spectra in the right way, you might even see a subtle 1.69 micron feature in the medium spectrum for Tara. This could be consistent with magnesium chloride or perhaps other salts. I remain completely agnostic to those sorts of details. Nonetheless, they've been mentioned in the literature. The key for me is that previous studies, notably VLT spectra that were presented in Ligier et al. 2016, showed that Europa's surface shows a clear deviation from water ice in the 1.7 micron range. And I think our results are broadly consistent with that. As that first bullet notes, yeah, organics can do some things in this wavelength range. I don't actually think we're seeing any hints of organics here. If what we're seeing at 1.7 microns was due to organics, I would expect to see more clear evidence for organic compounds at other longer wavelengths where organic features are quite strong, and we don't see any evidence for that in the JWST data. Also of note, we see a subtle 1.78 micron band that a variety of different hydrated species show a feature in this wavelength range. Of course, so does crystalline ice, so that kind of muddies the waters a little bit. But Ligier did note that where they see deviations in the 1.7 micron slope, they also note a subtle 1.78 micron feature. So I think broadly, we're seeing similar sorts of hints of something that's not ice happening in this wavelength range. Super vague, and I apologize for that. Perhaps more interesting is what's going on with Europa's 2 micron feature, where especially in Tara Regio, its central wavelength has shifted closer to 1.99 microns, which at first glance we thought was consistent perhaps with amorphous ice, which can shift this band to shorter wavelengths. But as I was discussing earlier, we know there's crystalline ice at depth everywhere across Europa. And in Tara in particular, we know there's crystalline ice at the exposed surface. So I don't think it's amorphous ice that's doing this. I think it's a contaminant that's shifting the 2 micron feature. This is not going to be a surprise for this audience. I'm sure most of you are aware that a variety of different salts can shift this feature, whether it's chlorides or sulfates. And so I think we're seeing hints of that in the Tara data. And now I want to switch to talk about the so-called, because it shifts a lot, 3.6 micron continuum water ice peak. This feature has been used in the literature as an ice thermometer, notably when you have mostly pure ice, which we'll come back to that. But just going on that assumption of, sure, maybe we can use this feature on Europa as a surface thermometer. We went down that rabbit hole for a little bit. And doing that, if you look at the central position of this feature in the north latitude ice rich zone, we back out that the temperature is approximately, in terms of how it compares to laboratory data, to 120 kelvins, which is in line with the peak day-side temperatures for Europa. So far, so good. But then the central wavelength shifts dramatically to longer wavelengths as you go to Powys and then you go to Tara. And suddenly, this would suggest that the ice in these regions is very warm. And this doesn't seem consistent with what we're actually seeing. So as a counterexample, the peak day-side temperatures for Callisto, the neighbor of Europa, are estimated to be about 170 Kelvin. And in JWST data of Callisto, we see a clear thermal tail start to pick up past about 4.5 microns. We see no evidence for this sort of thermal emission in the JWST data for Europa. So I don't think this shifting has anything to do with temperature. And again, instead, I think it's due to contaminant mixing. So some combination of salts. We also know there's a lot of CO2 in these regions where we're starting to see, where we see the shift to be more prominent, and also, of course, hydrogen peroxide as well. So now I just want to show some more spectral maps for some of these features. I'm going to start with the 1.5 micron band. I know I haven't talked about it, but I think it's worth including on this slide just to show that we did look at it. And the results for this are essentially the same as the 1.65 micron band that I showed you previously. The central wavelength doesn't change much at all, and it's stronger in the north latitude zone. This all makes sense to me. I think what's going on here is the 1.5 micron band samples relatively deep depths, deep for a spectroscopist. I know the geologists in the room are thinking, who cares? It's a millimeter. So similarly, I think the 1.5 and 1.65 micron band are sampling basically the same crystalline ice retained at depth. But then as you go to the 2 micron bands, now you're starting to sample shallower depths. Central wavelength is starting to get a little wonky. It's starting to shift around. It's still stronger in that north latitude ice rich zone, but the disparity between that zone and Tara and Powys is less. And then once you get to the 3.6 micron continuum peak, now we're starting to see some pretty wild things in terms of changes in the central wavelength, but it is stronger at northern latitudes, again, consistent with more ice up in that zone. And this oval just highlights, the main takeaway here is just how the central wavelength for these features can really change and deviate, not for the 1.5 band, but for the other features, how it can deviate from water ice as we've measured in the laboratory. And so in summary, for this part of the project, our results, our measurements are broadly consistent, I think, primarily with contaminant mixing with water ice in the regolith of Europa. I don't think we're seeing any trend or anything special going on in terms of surface temperature. I can't fully rule that out, but I don't think the results are consistent with that because, again, we don't see any evidence for thermal tail at longer wavelengths in the JWST data. All right, finally, I want to talk a little bit about solid state CO2 on Europa. I'm sure this audience has heard quite a lot about these features seen by JWST, especially the 12 CO2 feature, which shows a really interesting double lobe centered near 4.25 and 4.27 microns. But I want to focus a little bit more on the little guy next to them, this 4.38 micron feature that's attributed to the heavy stable isotope 13 CO2. So just off the bat here, going back to our regional spectra, there's clear differences in the spectral properties and the strengths of these CO2 features as we look at these different spectra. So I'm going to start with the 4.25 micron lobe. Note that the 425 and the 427 lobe were mapped by prior studies. So we reproduced that for the purposes of our paper. We don't see any deviations in our results from what was previously published. The 425 lobe is strongest in Tara and much weaker at northern latitudes. A similar sort of story for the 4.27 micron lobe, although note the drop off in the strength of this feature is more muted compared to the 4.25 micron lobe, and I'll come back to that on the next slide. And then for 13 CO2 ice, I think it's going to be pretty obvious what you're about to see. You can just tell by eye. We only reliably detect it at southern latitudes, primarily in Tara and Powys at the 3 sigma level. We really don't see it at northern latitudes at all. And so what exactly is going on here with 13 CO2? Its distribution, it's strongest where the 12 CO2 feature is strongest. That's not a surprise. 13 CO2 is a common, naturally occurring isotope of CO2. So at first glance, this all seems to hang together. But something of interest, of course, the 12 CO2 feature shows band splitting. It's got 2 lobes. We see no evidence of band splitting with the 13 CO2 feature. And so one thought here is that the 13 CO2 is actually associated primarily with one of the lobes and perhaps not with both. Based on comparisons to laboratory data, I would expect the 13 CO2 feature to primarily be associated with the 427 lobe, because we see both of these features go together, whether it's crystalline CO2 ice. I don't think we have CO2 ice on Europa, but just the lab data show that these 2 features go together, or whether it's CO2 trapped in water ice, which seems more likely for Europa, as that would be more stable at its peak day-side temperatures. And also in trapped CO2 ice, you'll see a 2.7 micron feature, which we've also detected on Europa. I'm not showing that here because it was published in previous studies. But the interesting thing for me is the distribution of the 13 CO2 actually seems to track more with the 4.25 micron lobe, not the 427 lobe. And in fact, where the 4.25 micron lobe is stronger, so where its band depth is larger than the 427 band, we see 13 CO2. And where that strength symmetry flips, strength ratio flips, we don't see 13 CO2. So we actually map, so all those spaxels you see on that map on the left, in all of those spaxels, the 425 lobe is stronger, and all the spaxels where you don't see 13 CO2, the 427 lobe is stronger. I don't have a satisfying answer for you today. We're at the stage, we put all this work together for the paper, looking at 13 CO2, and left the paper in a future work sort of mode where really we're dependent on the ongoing laboratory experiments that are looking at CO2 on this under conditions in the laboratory that are relevant to the surface of Europa to try and better understand the relationship between the double lobe 12 CO2 feature and 13 CO2 feature to see if we can unravel this mystery. And so summarizing here, I think CO2 is likely a good tracer of recent subsurface exchange, similar to the sodium chloride story. It's concentrated in the same regions, both the 12 and the 13 CO2, primarily in Tara. CO2 is super volatile at the peak day-side temperatures of Europa. It should definitely be removed over short timescales. It has to be replenished through one mechanism or another. If CO2 is primarily radiolytic on the surface of Europa, so if it's just carbon dust or something falling onto the surface of Europa and then you make CO2 in situ, I'd expect to find more CO2 at colder polar latitudes as opposed to at the warmer low latitudes. And that's the exact opposite of what we see. And so my suspicion is, and this is consistent with prior work put out by Trumbo and colleagues, as well as Villanueva and colleagues, and other studies, is either CO2 is directly coming out of Europa's subsurface and getting concentrated in Tara, or some other carbonaceous material is coming out of Europa's subsurface and then gets radiolytically modified into CO2. I remain a little bit agnostic about whether it's actually subsurface CO2 or just another form of carbon, whether that's organics or carbonates. Nonetheless, I do think subsurface CO2 or subsurface carbon is required in order to explain the distribution that we see. And again, this is broadly consistent with the story surrounding sodium chloride in Tara Regio. Okay, thank you.
Great, thanks, Richard. As a reminder, you can please put your questions in the chat, or at this point, if you'd like to unmute and ask your question, you can go ahead and raise your hand, and then we'll call on you as we get questions. We have plenty of time for questions and discussion, which is great, and this has kind of been our goal of recent Europa Clipper lecture series, to have slightly shorter talks and more time for questions and discussion, because that's been going really well for the past several. So feel free to ask any questions or discussion topics that you have. Okay, we'll start with a question that's in the chat from Caroline. Caroline, do you want to unmute and ask, or would you like me to read it? I'll give you 3 seconds. Okay, go ahead.
Okay, so for the first part of the regional difference in amorphous and crystalline ice, what is the underlying reason we suspect? Could it be, warm and fresh subsurface material exposed at different ages? And would that include that Tara Regio is younger than Powys?
That's okay. There's some interesting questions there. Some of that I'm going to punt on and let geologists answer that. As a spectroscopist, I'm focused on things that are skin deep. So some mechanism or mechanisms have to be preserving crystalline ice at depth, whatever's involved in that. The charged particle story, or part of this, is because that ice is at depth, it's going to take longer to amorphize it. And so the recrystallization processes at depth are just more efficient. That's my off-the-cuff response to that. And I'd let some magnetosphere type people try and give a more nuanced answer to that. In terms of your second question, that's more that's a more exciting question. Is the crystalline ice signature stronger in Tara? Well, if the hypothesis we put forward is correct, the answer to that would be no. The answer to that would be if Powys was near the center of the observation, the crystalline feature would be stronger than what was observed. And this is testable, clearly, because we have more data.
Very interesting. Yeah. Okay, so this might be an observational bias.
Yes.
Okay.
I suspect that's exactly what it is. It's an observational bias. But that's a provocative answer, so we didn't put it in the paper.
Okay, thank you.
Yeah.
Great, thanks. Al, you have your hand raised. Go ahead.
Yeah. Great talk, Richard. I have two connecting question. One is that 1.65 micron absorption band. Is that like distinctive to crystalline water ice as well, only, or it can be for other species as well? For instance, if you have like ammoniated water ice brine, it can also show like 1.65 micron. Also, if you use the Mastrapa's optical constant amorphous water ice, when you use widely used Hapke model, it sometimes produce also that 1.65 micron absorption band. So 1.65 cannot, from my perspective, be given only to the crystalline water ice. Another connecting question is the Mastrapa's optical constant at 3 micron. There is a paper, Roger Clark, 2012, showed that using Hapke model and their optical constant, there is a discrepancy between the real reflectance spectra, at least at 120 Kelvin, to the optical constant of 120 Kelvin using Hapke model. So how do you explain that when you use the optical constant of Mastrapa, particularly that 3.1 micron absorption band is very close to the anomalies that Roger Clark has found in the laboratory, and that can be also connected to the NIRS data, because NIRS might have like two detector within this area, 3.1 micron area. I'm not exactly sure whether that region is the area between two detector, which might give like very noisy data. That's why we didn't find 3.1 micron absorption band in NIRS data, even though it might be there. It's because the data, the way detector are organized. I'm sorry for asking a lot of questions together.
And I can give you some good answers and also some half-baked answers to some of that, especially since I'm not a lab spectroscopist. So I might defer to some others. For the 1.65 band, I completely agree with you, because it's probing deeper depths, you've got volume scattering going on. So yeah, there's going to be other things that are going to contribute to it. The thing that sticks out to me is that the wavelength range, the central wavelength of the feature doesn't seem to shift at all. And I've seen this both in the IRTF data and now in the JWST data. It's really locked onto a specific wavelength. So that's kind of where I hang my hat as a spectroscopist. But you are correct. I mean, frozen salts, right? It's got water in it. If you freeze salts, you're going to make ice. So yeah, I'm not surprised. And I've seen it in the laboratory literature, so I know what you're talking about. Like, is it sylvite, right? Frozen potassium chloride looks almost identical to water ice. So your point is extremely well taken. In terms of the Fresnel region, I'm less concerned about that because it's so sensitive to reflection of ice grains and the exposed surface. I'm pretty confident that we are sampling crystalline ice, and this is kind of the half-baked answer in that. So I've noticed, I've been around a little bit now, and I've noticed a life cycle, and I'm sure it's not just in the optical constant world, it's kind of everywhere, where a new set of optical constant comes out, everyone's excited about them, a few years go by, and then everyone's like, well, they're not perfect. And then maybe a decade goes by and everybody says, oh, we need to replace these. And so I think the Mastrapa optical constants, and I don't mean to speak for the community here. This is just my own perspective on them. They've done an absolutely wonderful job to this point, but I think it's time for a new set of water ice optical constants. So I'm not really answering your question. I am sidestepping it, but I take your point that the Mastrapa optical constants are not perfect in the 3 to whatever 3.5 micron range.
Great, thank you. Murthy, you have your hand raised. Go ahead. Murthy, we can't hear you if you're speaking, but if you have a question, go ahead. Oh, now we can hear you.
Now I'm speaking. Sorry, I unmuted myself. So yeah, wonderful work in NIRSpec also what you have shown. There are a couple of things that we need to probably be more quantitative than shallow and deeper, even for spectroscopists. If you look into page, 49 of SSR composition, we have approximate skin depths of wavelengths given. And the difference between the 3 micron region and probably 1.65 micron region is between approximately 1 micron to probably 100 micron. And the main difference that we see there, if you look into that figure, is that oxygen and sulfur are the ones which probably are stopped at shallower depths of 1 micron, whereas protons and electrons pass through to the deeper ones. So one needs to really be careful in saying that amorphous ice, porous ice probably crystallizes faster. We need to be a bit more careful and a bit more quantitative about it. And the information is available already in the literature. Okay, that's the first thing. Okay. Second thing that surprises me is about the lack of 13CO2 band. Again, we published the data, not necessarily, I think, Sam knows about it, not necessarily, aimed at Europa, but in RSC in 2023, we published that data of CO2, which has 2 absorption bands, different ratios, but they're exactly reproduced in the 13CO2 bands. A lack of 13CO2 is very important. In fact, if it is not because of your signal to noise ratio problems. If there is a signal to noise ratio problem, then we are actually interpreting too much out of nothing. But if it is indeed that one of them is missing, that would mean that the 13CO2 is depleted from the source that generated CO2 main peak, or one of the 2 CO2 peaks is not from CO2. So we are in deep problems here. Before getting too much into it, one needs to really be sure that certain CO2 is indeed completely absent for the second peak.
Yeah, that's a great point. And Samantha's got a lot of other data for the rest of the surface of Europa, so it'll be interesting to see what 13 CO2 looks like on the transitional longitudes as well as on the trailing side, if it's there at all.
Yeah, it is extremely unlikely that 13 CO2 for another band is missing. And it is probably, I think one needs to revisit this before concluding. And once it is confirmed, then we have a lot of problem with that. Yeah,
that's great points.
Thank you. Wonderful data. Thanks a lot.
Yeah.
Great, thanks, Murthy. There's another question that just appeared in the chat, but I'm going to go ahead and ask the question that I have. And Richard, I was wondering, you alluded to a bit, perhaps future JWST observations. Can you tell us a little more about what is planned, or what you can tell us about what is planned?
Well, the data are public. It's data that Samantha's been collecting for the last couple of years. And I know that that group is working towards publication. They presented at DPS last year.
Great.
I don't know if Samantha's on the call and if she wants to chime in about that, but
In the meantime, John Spencer, you have a question in the chat. Would you like to unmute yourself and ask it? Otherwise, I'll read it out. Go ahead.
Yep, sure. This is great stuff. I was just wondering how strong an evidence for internal replenishment the presence of CO2 on Europa is, given, of course, that we also see CO2 on Callisto, where it's unlikely to be actively replenished from the interior.
Yeah, John, that's a great question. For me, the thing that I am hanging my head on for now is the spatial distribution of the CO2 features, with it being in and around and highly concentrated in Tara, which is where we see the irradiated sodium chloride. And then we go to northern latitudes where it's colder, and I would naively expect to find more CO2, and it's in fact very weak at northern latitudes in the ice-rich zone. And so putting that together, I think the source of the CO2 is in Tara. I assume that's from subsurface material because the CO2 can't stick around for that long, certainly not over geologic timescales. So it has to be replenished through one mechanism or another. If it was, so, you know, the alternative might be like, okay, maybe it's sea-rich dust that's falling onto the surface of Europa, mixes with water ice, and then you make CO2 molecules in situ. Why would that dust be concentrated in Tara? I can't wrap my head around that. I think a geologic, well, I don't want to use that word, a subsurface origin for the CO2 makes more sense.
Yeah. Okay.
Sorry, struggling to unmute. Great, thank you. Any other questions or comments or discussion topics for Richard? I think I've waited the 7 or 8 seconds of silence. So we'll go ahead and thank Richard again. Thanks so much for joining us and for presenting this. I know we've been trying to get it on the schedule for a while, so I appreciate you finally getting to be here to do that. Just a reminder for everyone else, we have a schedule that's quickly filling up for the Europa Clipper lecture series for the rest of the year. If you have any suggestions or talks that you would like to see, please reach out to Kate Kraft and myself, and we'll try and see if we can fit those in on the schedule. And we'll see you again on February 10th for our next installment of the Europa Clipper lecture series. Any last words, Kate?
Sorry, and I have the microphone on the other location, so it might be hard to hear me. But Karen, can you just quickly remind everyone too where talks or recordings are posted?
Yes, we are actually working on getting the recordings posted in a new location on a PSI, hosted through PSI on a YouTube site so that they will be more publicly available to everyone. So we'll let everyone know when that is up and working and happens. And yeah, hopefully we'll be able to get those recordings to you in a more efficient way soon.
Great,
okay.
Thanks, and thanks so much, Richard. Really great talk.
Yes, thanks, Richard. Thanks, everyone.
Yeah. Thanks for having me.
Happy New Year. Kurt, yeah, there's not a calendar invite yet, but they'll be going out soon. We're going to send out placeholders for the rest of the year soon. Thanks.
I talked with you are.